Hello, ladies and gentlemen. Today we are going to be graphing logarithmic functions. Our learning target is to be able to graph logarithmic functions with transformations and identify the inverse relationship between exponential and logarithmic functions. Let's start by looking at the definition of what a logarithm is if we're looking at a logarithm with a base b. So let b and y be positive numbers where b is not 1. The logarithm of x with base b is denoted by log base b of x and is defined as follows. Log base b of x equals y if and only if b to the y equals x. The expression you see is read as log base b of x. So here's an example. If log base 3 of 27 equals y, then 3 to the y equals 27. Hence, since 3 to the third equals 27, then log base 3 of 27 equals 3. Notice the inverse, that this is an inverse of an exponential function. A logarithm is an exponent. Here is our log. Notice log base 3 of 27 equals y. The log is the exponent. When you are asked to find a log, you're given a base and an answer. Therefore, hence, you're finding the exponent. To evaluate a log, try thinking about exponents. You can also rewrite an expression from logarithmic form to exponential form to determine the exponent. So as you see, we have log with a base of an argument, which is the number, which equals the exponent. So if it makes it easier, you can rewrite it in exponential form as b to the y equals x. Notice if there is no base given, the base is assumed to be 10. And because the value of a log is an exponent, you can only take the log of a positive number. So let's look at a couple of examples where it might be helpful to write a log form into exponential form or vice versa. In example A, we're given log base 2 of 8 equals 3. To rewrite that in exponential form, we would say 2 to the third equals 8. And log base 3 of 9 equals 2, hence 3 squared equals 9. Now let's go backwards. We have 8 to the 0 equals 1. Well, our base is 8. So we have log base 8. The number, the value is 1, so of 1 equals 0. And a good way to check that, 8 to the 0 equals 1. Next one, we have 5 to the negative 2 equals 1 over 25. Well, our base is 5, so we have log base 5 of our value, the number 1, we'll put that over in parentheses, 1 over 25 equals negative 2. And if you work that back, 5 to the negative 2 equals 1 over 25. Now let's take a look at the relationship between the logarithmic function and the exponential function. If you notice, the exponential function is reflected over the line y equals x to create the logarithmic function. Hence, they are inverses of each other. We might recall that in order to find the inverse of a function, we switch the x and y. Hence, we are also switching the domain and range, and where we have a horizontal asymptote with the exponential function, we have a vertical asymptote with the logarithmic function. In this slide, we're going to look at the difference between two log functions being graphed. The first one on the left, which would be a basic parent function, f of x equals log base b of x, and in this particular case, where b is greater than 1. When that happens, we will have our vertical asymptote at x equals 0, and if you notice, the graph goes up to the right. However, in the next graph, our base, there's our base. Our base here is between 0 and 1. That indicates that the base is a fraction. All right, when b is a fraction, that causes a reflection over the x-axis. And with that reflection over the x-axis, now we still have the vertical asymptote at x equals 0. But our graph now goes down to the right. Okay, let's graph an example here. We have y equals log base 2 of x. We're going to find some exact points using an xy table. But since we have log base 2 to the x, it might actually be easier to convert that to exponential form. So that would give us 2 to the y equals x. Notice in this situation that y becomes the independent variable and x the dependent. So we would want to choose values for y to put into this, and typically this is a parent function. We would choose the values -1, 0, and 1. So when we substitute in here, 2 to the -1 is 1/2, 2 to the 0 is 1, and 2 to the 1 is 2. Now we know we have a vertical asymptote where x equals 0. So we're going to go ahead and draw that in, and we'll put that right here. And now we can plot these points. So we have 1/2, -1. We have 1, 0. This is a critical point that we like to use and look at. And we have the point 2, 1. We could continue on, but this gives us an idea of what our graph is going to look like. So we're going to draw our graph as best as we can. Now, to find the domain, well, what x values exist on this graph? Well, we cannot go as far as the vertical asymptote, so our x values are going to be x is greater than 0. Our range will go down to -infinity, and as we go up to the right, we will go to +infinity, so our range is all reals. Because from left to right, we are going up, the function is increasing. Our end behavior, as x is approaching -infinity, meaning heading to the left, our y value is approaching what, and I probably should have looked at this a little bit better and said it differently, as f of x approaches -infinity. So that means as y approaches -infinity, x is approaching 0. As y continues to go further and further down, I'm getting closer and closer to that vertical asymptote, but not quite getting there. Now as f of x, meaning y, approaches positive infinity, our x is also approaching positive infinity. Now let's take a moment to look over the transformations, the same transformations we have been performing for all of the other function families. If a is less than 0, we reflect over the x-axis. If the absolute value of a is greater than 1, we have a vertical stretch. If a is between 0 and 1, meaning a fraction, we have a vertical compression. Please note that if b is a fraction, that will also cause a reflection over the x-axis. H still determines our horizontal translations, and in this particular case, H will also determine our vertical asymptote, which is at x equals h. And do not forget that h is always the opposite sign from the equation. Our vertical translations are still controlled by k. If it's positive, it goes up, and negative, it goes down. As we found with the exponential functions, there are many ways that you can graph these functions, and one of the transformational approaches, if you wanted to just do a rough sketch, you would focus on that critical point we spoke of, the 1, 0. And that's for the logarithmic function, and apply the transformations of a, h, and k. Make sure that you always graph your vertical asymptote. Or you can make a table for the parent function, then multiply the value, the y value, by a. A affects the y value, the value of the function. Apply k to the result of your y to get your new y. Apply h to the x value to get your new x. And then plot your new xy coordinates and your vertical asymptote to draw the graph. Okay, let's try the transformational approach with this graph function right here. Y equals 2 times log base 4 of x plus 4 plus 2. Let's first identify our values of a, which is 2. Our base is 4. H is negative 4. Remember, always opposite sign. And k is 2. So before we know anything, we know that we're going to have a vertical stretch, we're going to be going left 4 and up 2. All right, so we're going to start with graphing the parent function and creating an XY table for that parent, which will be y equals log base 4 of x. Okay, without any of the transformations with that. Keep in mind that this can be rewritten as 4 to the y equals x, if that helps you. So again, with the logarithmic function, we put in values for y, not x. So we're going to use that same negative 1, 0, 1, and you'll get very familiar with this. So if I looked at the exponential form, I would say 4 to the negative 1 is 1/4. 4 to the 0 is 1. And 4 to the 1 is 4. Now that we've done that, we're going to apply the multiplier of 2, meaning the value of a. So we're going to take that y and multiply it by 2. So that's going to give us 2 times negative 1 is negative 2. 2 times 0 is 0. And 2 times 1 is 2. Now we're going to work with the vertical translation of k. So we're going to apply k. So that means we're going to add 2. So negative 2 plus 2 is 0. 0 plus 2 is 2. And 2 plus 2 is 4. And we have one last thing to do. We need to apply the value of h. So we're going to take that x value. Since h is negative 4, we're going to subtract 4 from that h. Well, 1/4 minus 4 is going to leave me with a negative 3 3/4. 1 minus 4 is negative 3, and 4 minus 4 is 0. The values in this are resulting x column and resulting y column. Those are our coordinates that we are actually going to graph here. So we're going to be graphing the points negative 3 3/4, 0, negative 3, 2, and 0, 4. All right, let's see what that looks like. So negative, and let's talk about our vertical asymptote, by the way. Our vertical asymptote is going to be at x equals h. Let's see where we can. So in this case, it will be x equals negative 4. So let's go ahead and draw that in. It's always good to have our asymptotes drawn. It gives us some kind of guidance as to what our graph is going to look like. All right, so plotting our points, negative 3 3/4, 0. We're somewhere around here. Negative 3, 2. I should probably be using a different color than the asymptote. And 0, 4. So if we follow those points, we know as we go down to negative infinity, we'll get closer to the asymptote and then up and to the right. And that is our function. Notice if we had taken that critical point of 1, 0 from the parent function and shifted it to the left 4 and up to 1, 2, 3, 4, 1, 2, there's that critical point right there. And the only difference is that our graph is going to be a little steeper because the value of a was 2. Now that we have our graph drawn, we can answer the rest of the questions. So we already found the vertical asymptote. We needed that when we graphed it. So that was x equals negative 4. So remember that the vertical asymptote is x equals h. All right, which means that our domain must be all the x values greater than negative 4. So x is greater than negative 4. Our range is all reals. The function is from left to right is going up, so we are increasing. F of x, we'll just replace that with a y. As y is going to negative infinity, our graph is approaching x, the coordinates, x coordinates, excuse me, are approaching that negative 4. And as f of x, meaning y, is approaching positive infinity, meaning as the graph is going up, then x is approaching positive infinity as well. Okay, let's do one more and take the same approach. So we're going to start with making an XY table. for the parent function. Now we should identify our a is -2, our base is 4, h is +4 this time because it's x minus 4, and our k is -2. So we know we're going to have a vertical stretch because a is -2, but we're also, so vertical stretch, we're also going to reflect over the x-axis because of the negative a. I'm going to run out of room there, so let me do that here. Okay, and I'll just give myself some more room here. Bring this down a little bit. All right, so this is going to be our xy table for the parent function of y equals log base 4 of x before we perform any transformations to that. And again, remember that that can be rewritten as 4 to the y equals x. So once again, we're going to put those same values into our table. In for the y values, -1, 0, 1. Our x's again, so 4 to the -1 is again 1/4. 4 to the 0 is 1, and 4 to the first is 4. This time we're going to apply the value of a, which is -2, so we're going to take that y and multiply it by -2. So -1 times -2 is +2, 0 times -2 is 0, and 1 times -2 is -2. Now we'll apply the value of k, which is -2. So this was a, this is k. So 2 minus 2 is 0, 0 minus 2 is -2, and -2 minus 2 is -4. Now let's apply our value of h. Since h is a +4 this time, we're going to add 4. So this is h. So 1/4 plus 4 is 4 1/4. 1 plus 4 is 5, and 4 plus 5 is 9. I take that back. I wasn't adding the 5, I was adding 4. I looked at my chart. So 4 plus 4 is 8. Okay, so what's our vertical asymptote going to be? Our value of h is 4, so hence my vertical asymptote is x equals 4. So let's go ahead and draw that. And now we can plot our points, the resulting x and y, after we performed all the transformations to it. So we have a point at 4 1/4, 0. Let's get that other color. We have a point at 5, -2. And we have a point at 8, -4. 1, 2, 3. And now we can draw that graph. And you can see the reflection of this graph over the x-axis. Once again, if we were doing a very rough sketch, we could have used that critical point of 1, 0, and we would have been reflecting over the x-axis. We had a horizontal shift up to the right for 1, 2, 3, 4, down 2, Hence, we have this critical point right here, and we would have known to draw our graph down to the left because A is negative. Now that we have the graph drawn and our asymptote drawn, we can apply and look at the following properties. So the vertical asymptote, which we already found in order to draw our graph, is x equals 4. Our domain, hence, is all of the values of x greater than 4. Our range is still all reals. The graph in this situation from left to right is going down, hence it is decreasing. And as f of x, again, we are talking about y, as y is going to negative infinity, our x is actually going to continue to the right to positive infinity. And as f of x, or y, is approaching positive infinity, meaning as y is going up, x is approaching that asymptote of 4. Well, that concludes our lesson for today.